Hello everyone, this is the walkthrough of week 4, problem 2.2. Let n greater than or equal to 2 be a positive integer. Let p be a prime that is greater than n. Find all polynomials q of x of degree at most n in GFP, such that x minus 2 times q of x is equals to x times q of x minus 1. So this is really the formula we need to focus about, this one. So we need to derive some properties of q of x to be able to find all of the possible polynomials q of x. So what are the properties of q of x? First of all, we notice that there are some numbers that you may notice. First one is x minus 2, x, and x minus 1. So if x is greater than 2, then all of the x minus 2, x, and x minus 1 will be positive or 0. So in this case, it's much easier for us to deal with. But if x equals to 0, 1, or 2, things can be more complicated. So we'll start from here. We first plug in x equals 0 and see what it gives us. So it becomes minus 2 q of 0 is equals to 0. Right? And this gives us q of 0 equals 0. Right? And which tells us 0 is the root of q of x, which means that q can be written as x times q1 of x. Because 0 is the root, so x is the root of q of x. And also, and this also tells us q of x minus 1 is equals to x minus 1 q1 of x. Q1x minus 1. We just like substitute this x with x minus 1. And this gives us this formula. Yeah. And then we can plug in this x and this x minus 1 into this formula. And it gives us x minus 2 times x times q1. Yeah, this is q1. Oh, no, sorry. Nope, this is q of x. Yeah, because this is the original q of x. But we are finding a root of q of x. So we can replace q of x with q1. And we plug in this q of x and q of x minus 1. This gives us x minus 2 times q1 of x is equals to x times x minus 1 q1 x minus 1. So we are already getting some process of understanding the properties of q. Next, we can plug in x equals 1. And it gives us minus 1 times q1 of x. Nope, yeah, it is 1. Minus 1 times q1 of 1 equals to 0, because this term is just 0. This tells us 1 is the root of q1. So q1 has a factor of x minus 1, which means that q1 can be written as x minus 1 times q2 of x. And equivalently, q1 of x minus 1 is equals to x minus 2 times q2 x minus 1. And again, we plug in this this to q1 with q2 instead. And we write the formula. It gives us x minus 2 times x minus 1 q2 of x is equals to x times x minus 1 times x minus 2, q2 x minus 1. And the crucial fact you need to notice is that this part and this part are just identical. So the only difference is this is q2 of x and this is q2 of x minus 1. So that is the difference. So for this one, if we plug in x that is greater than 2, so because if we plug in 2, then it will be 0 on both sides. So it doesn't tell us anything. But if we have plug in x which is greater than 2, so we can get q2 of x is equals to q2 of x minus 1, because the other term are just identical. And this holds for all of the x greater than 2. So we can get q2 of 2 is equals to q2 of 3 equals to q2 of 4, blah, 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 all the way to q2 of n. Where c is the constant. So how many points are this? Because we are starting from 2 and anyways n, so there are n minus 1 points in total. But because q is because we are given a function, q of x is of degree at most n. And for q2, we are already separating 2 degrees out of q. So q can be at degree at most n minus 2. So we have q2 of x has degree at most n minus 2. And also we have n minus 1 points, which is constant. So this tells us Q2 is just a constant. Like you can draw some examples to show that the case. The simplest example is for if you're given 2 points, then you determine a line, right? And also this conclusion can be extended to other degree for even larger n. So right now we have Q2 is a constant, and then we can then solve the expression of Q. Because we know Q of x, it have a root which is 0. This is given by this part. So we know Q of x is equals to x times some Q1 of x. And from this part, we know Q have a root of 1. So we can further split Q1 into x minus 1 times Q2. And we know Q2 is a constant. So this equals to Cx times x minus 1 for some constant C. And this gives us the overall expression of Q of x. And this is also complete, meaning that we have found all of the polynomials that satisfy the requirement.